Hello everyone. We're discussing adiabatic process and we have developed PV gamma constant where gamma is Cp upon Cv and is always greater than 1. Now get me a relationship between P and temperature and V and temperature for an adiabatic process. If relationship between pressure and volume is PV gamma constant, then what is the relationship between pressure and temperature and volume and temperature? Answer this in the comment box. Look, what is PV? nRT for any type of process. PV gamma is constant. This is for an adiabatic process. Group this and you will get the answer. The first is we need a relation between pressure and temperature. To do what? What is V? N R T divided by P. Put this V in this and you get what? P V gamma. This is V. N R T upon P to the power gamma is some constant C. P multiplied by V to the power gamma. V is nRT upon P. What is this? P to the power 1. This is P to the power gamma, which becomes what? P to the power 1 minus gamma, T gamma. Now, this is N to the power gamma, R to the power gamma. Everything is what? A constant. N is a constant, R is a constant, gamma is a constant, this is a constant, and therefore everything is basically what? A constant. The things which are going to change in an adiabatic process are what? Pressure and temperature. So what we have done, this is P to the power 1 and this is P to the power gamma, which becomes what? P to the power 1 minus gamma, T to the power gamma. This gives us a constant. This is the relationship between pressure and temperature. So if you remember PV gamma constant, that is more than sufficient, because with the help of PV equals to nRT, you can always develop these types, these functions, these relationships. Now, do it fast. Get me relationship between volume and temperature using the same method. This time let's replace P with N R T upon V. We need relationship between V and T. P is nRT upon V. P N R T upon V multiplied by V to the power gamma multiplied by V to the power gamma. This thing is a constant. T, this is V gamma, this is V to the power 1, which is what? V to the power gamma minus 1. N is a constant, R is a constant, C is a constant, C divided by NR is another constant. Just don't think that this is the same C. C stands for what? A constant number. So C divided by NR is another constant, which gives us this relationship. Put these results inside a boundary. If you wish, you can remember these, or just remember PV gamma is a constant, and you can always find things like these. Write down degree of freedom. This is basically coming from kinetic theory of gases, but you can easily understand this part, and it is useful in thermodynamics. So, as I had told you, that we'll be discussing part of thermodynamics, bit of kinetic theory of gases, a mix of all these things, so that you can feel and understand each and everything. Degree of freedom represented by small f. What is degree of freedom? You have a molecule, a gas molecule. First, very elementary case, a single atom. Assume a sphere, a point basically. So this is an atom, and this atom can move along the x-axis, along the y-axis, and along the z-axis. So we say that it has 3 degrees of freedom. That means there are 3 modes in which it can have kinetic energy. So, how many modes are there in which it can have its kinetic energy? X, Y, and Z. These are called what? Degrees of freedom of a monoatomic gas. For example, helium. For example, argon. Again, different types of modes in which a gas molecule can have its energy, total energy. What is total energy? I hope you remember U, that NCVT part. That energy, if you remember, I had told you was basically what? Kinetic and potential energy. Right now, if you have a single molecule, you're talking about what? Kinetic energy only. So this thing has what? Kinetic energy along the x-axis, kinetic energy along the y-axis, kinetic energy along the z-axis. And therefore we say there are 3 degrees of freedom. Now, this molecule or atom as a sphere can also rotate. And if things rotate, They have what? Rotational kinetic energy. What is translatory kinetic energy? Half mv square. What is rotational kinetic energy? Half I omega square. Now let's focus on this half I omega square part. This I is basically of mr square type with a coefficient. If you consider atom as a hollow sphere, 2 by 3. Solid sphere, 2 by 5. Now, what it should be considered, I will leave it to you because you are intelligent enough. But we are not into that. We are into what? mr square portion. Now this r is very, very small. R of an atom is very, very small, and therefore square is even kind of negligible thing. So this half I omega square term is approximately what? 0 as compared to what? Translatory kinetic energy of an atom. Now you can always say that mass is also very small, so it should also be very negligible. The point is that you're comparing half mv square and half I omega square. In this I, you already have what? M. But apart from m, you have the term of r square, which makes it what? Almost negligible. That's the reason this half I omega square, or contribution in kinetic energy due to rotation, is negligible. Which means if you have a monatomic molecule, for example helium or argon, then degree of freedom is what? 3, corresponding to what? Kinetic energy along the x-axis, kinetic energy along the y-axis, and kinetic energy along the z-axis. Note down this data, also this information, and then we'll write few statements. Write down the statement. Different modes in which a gas molecule can distribute its energy is called degree of freedom. It's called degree of freedom. For a monatomic gas, molecule, inside the bracket, a point mass. When you say point, you can understand better this half I omega square. Now, let me explain this thing again. You have an atom of hydrogen, suppose, not H2, H. Suppose you have an atom. Now, that atom is what? A nucleus surrounded by what? Electron cloud. So when you talk about its mass of that atom, it is mostly in the nucleus only. That electron cloud is almost what? It's very light as compared to nucleus. So when you say M, you're basically talking about the nucleus part. Then what is R? Mass of the nucleus, R, is also technically radius of that nucleus. And therefore, this term is almost what? Negligible. So, how can you feel if things are negligible? You better say that a monatomic gas molecule is nothing but a point. Which point? That nucleus. So write down the statement. Molecule of a monatomic gas can have kinetic energy, can have its kinetic energy along the x-axis, y-axis and z-axis, and therefore its degree of freedom is 3. Contribution in kinetic energy due to rotational motion of the molecule, contribution in kinetic energy due to rotational motion of monoatomic gas molecule is negligible and therefore is not used. It is negligible as compared to half mv square. This half mv square is negligible to what? Kinetic energy of a moving ball. If you have a ball, cricket ball or anything, if you throw it, if you compare kinetic energy of that moving ball and this half mv square, this thing is almost what? Negligible. So the thing is that it's a relative thing. As compared to half mv square, half I omega square is what? Negligible, and therefore there are only 3 modes in which helium, argon or single atom gas can have its energy, and therefore degree of freedom is what? 3. Write down degree of freedom of a diatomic gas. This helium thing is just this, an atom, a single ball, very small. Diatomic. If we talk about diatomic gas, for example, H2 or N2, a very simple model will be this. This is HHNNOO type of thing. Now, let's talk about its degree freedom. Anything can move along what? X-axis. It's a dumbbell shaped thing. This diatomic molecule is what? A dumbbell shaped thing. So this is the bond and these are the atoms. So this thing can move along the x-axis, along the y-axis, along the z-axis. The usual 3 degrees of freedom are already present. But this time, let's see and let's talk about half I omega square. This dumbbell shaped molecule, now look carefully, it can rotate like this rotation. It can also rotate like this. I hope you can see the change in axis of rotation. When I rotate it this way, this is the plane of rotation. Is the axis of rotation perpendicular to the plane. So if I am rotating it this way, it's like rotation axis is what? Y-axis. If I rotate it this way This is the plane of rotation. This is the axis, which is z axis. So you have a z axis rotation. There must be x axis rotation also. What is that? This is the x axis rotation. So I'll be asking you a question, and therefore look carefully. You've got two balls connected by a massless rod, which is the bond length, and then the whole body is rotating along the x-axis, about y-axis, about z-axis. What do you think, which axis is going to give us negligible kinetic energy, and which are those axes whose kinetic energy, even rotational, should not be neglected? Can you answer this? Answer this in the comment box. I hope you can see these two balls. They are like nitrogen and connected by a bond length. Now, it's difficult to give you an exact estimate, but something which can make you comfortable is this. If this is the size of nucleus, then that's not how they are arranged. It will be something like this. As compared to radius of the nucleus, the bond length is much larger. I hope you understand this point. So if this whole size, this tiny ball, it represents what size of the nucleus of nitrogen atom, another nitrogen, then in N2, bond length is much larger. Now, it tells us what? Visualize these things. If I rotate the whole setup along the x-axis, if you can see the rotation which I am producing, basically like this, along the x-axis. Now, if you are rotating these things along the x-axis, if I zoom in, you get this. So this thing is rotating this way, individual atoms. So about x-axis, you're basically talking about half I omega square, I of mr square type, where r is radius of the nucleus, which is negligible, and therefore forget about it. But जैसे ही हमने y-axis की बात की, now this is rotation about y-axis. I hope you can see this is the rotation. So for this rotation, let me give it about z-axis so that you can easily see the rotation. About z-axis, this is the rotation. So for this rotation, we'll be again using mr square. But what is the r? R is half of bond length. So for this rotation, if I introduce half I omega square, then I'm not talking about I of this. I'm talking about I of a point mass about this axis. This is what is the R. Not the radius of the atom, but radius which is half of the bond length, which is not small and therefore cannot be neglected. Which means when you talk about kinetic energy rotational of a diatomic molecule, then out of 3 axes, 1 axis is useless. There are 2 which are contributing in degree of freedom, which are contributing in kinetic energy, and therefore they must be used, giving us a total degree of freedom 5. Before I continue this thing, tell me, do you understand this 2? Why it should be present? Why it should not be 3? It should only be 2. Are you comfortable with this part? Yes or no? Write down fast in the comment box. Write down the statement. For a diatomic gas molecule, apart from 3 translatory kinetic energy modes, apart from 3 translatory kinetic energy modes, 2 rotational kinetic energy modes are also present, in which axis of rotation in which axis of rotation is perpendicular to the bond length, in which axis of rotation is perpendicular to the bond length. We can see blue and red colors. Nothing special. This is a molecule. The red line vertical. This is a dumbbell shaped molecule and this is the axis. So about this red axis, molecule is going to rotate this way. About this, this is the molecule. The second axis shown in blue is this. About this blue axis, the molecule is going to rotate this way. It is shown by this blue arrow. About the green one, if you can see the color, this green rotation about the green axis which is passing through the bond itself, contribution in kinetic energy is what? Negligible. And therefore only 2 degrees of freedom because of rotation are present. If you wish, you can show these different axes of rotation. The red one, the blue one, and the green one. About the green one, rotational kinetic energy is approximately 0 or negligible. We are interested only in the blue and the red ones, giving us a total degree of freedom 5. Now, write down next. For a diatomic gas molecule, with vibrations at extreme temperatures, extremely high temperatures, a diatomic molecule is going to do this. It's going to oscillate. That's called what? Vibrational mode. Write down this. For a vibrating for a vibrating diatomic molecule, for a vibrating diatomic molecule, inside the bracket, at extreme temperatures, at extremely high temperature, even low is called extreme, so remember extremely high temperatures, bracket close, due to vibrations, due to vibrations. Now if you talk about vibrations, can you tell me vibrations will produce how many energy modes? Who can answer this first? Who can answer this thing first? If we introduce concept of vibrations, and the hint is connect these two balls with a spring. Now the spring is being compressed. So when it is being compressed, again and again, compression and elongation, if these things are happening, then how many energy modes you are introducing? Good, बहुत सही, 2 modes. Everybody has an idea of oscillations. In oscillations, there are 2 types of energies involved, kinetic and half kx square type of thing, which is what? Potential energy. So when a molecule starts oscillating, starts vibrating, we add 2 more energy modes. This is diatomic. You can add diatomic without vibrations. Without vibrations. Diatomic with vibrations. At extremely high temperatures, degree of freedom is what? 3 for translatory, 2 for rotational, 1 for translatory vibrations, another 1 for the potential energy part. So these 2 are coming because of what? Vibrations. Half mv square, which is different from this v. Remember, this 3 is because of what? Movement along the x-axis, movement along the y-axis, movement along the z-axis. This one is for this movement. And when you have a spring and 2 balls are connected and the thing is oscillating, you're talking about translatory kinetic energy and that half kx square, giving us a total of 7 as degree of freedom. But now remember one thing, if they give you a question and they say that you've got oxygen, if you've got hydrogen, if you've got nitrogen, and they do not mention anything else, you will be considering what? Diatomic gas without vibration, because these vibrations are present and will contribute only if you create very high temperatures. So in normal condition for a diatomic gas, always go for a degree of freedom which is 5. Note on this and then write a statement. Write down the statement. A vibrating molecule has vibrational kinetic energy and also has vibrational potential energy. thus giving us two additional degrees of freedom, thus giving us two additional degrees of freedom, and therefore total degree of freedom is 7. If you go for a molecule which has more than 2, then things are very complicated. So they will give you, if in any case they ask you a question, for example for H2O or something like that, then there are so many axes of rotation involved that they will give you a general idea of degree of freedom. We are interested in what? Monatomic and diatomic. Mostly diatomic without vibration. If they mention vibrations, then take what? Degree of freedom as 7. Now, the useful thing and important thing, why did we introduce the concept of degree of freedom? It will be used in this part. Write down a statement. There is a law of equipartition of energy. You don't have to worry about it. Just a statement for you. Law of equipartition of energy. Let me give you a feel of equipartition of energy with the help of monatomic, and then you will remember it for everything. So we have a spherical ball and there are billions and billions of these balls, tiny atoms, in a container. So what do you think, in which direction they will have more kinetic energy? Along the x-axis? If you find kinetic energy, if you take component of the V's along the x-axis of each and every molecule which is present in the container, remember there are billions and billions and billions of these molecules present, and if you take the velocity components along the x-axis and you find the kinetic energy, similarly you do it for the y-axis and then you do it for z-axis. My question is, in which direction you are going to find that more kinetic energy is present? Along the x, along the y, or along the z-axis? Answer this part fast. Good. For a container and for these small molecules, every direction is what? Identical. थोड़ा सा हम ये सोच सकते हैं कि because of gravity they will be coming down, but that effect of gravity is almost negligible on them. So you can forget about effect of gravity. That effect of gravity is gone. Once it is gone, it's very negligible. Then x, y, and z, everything is what? Identical. That means these molecules are going to have equal energy in all the energy modes. For x mode, for y mode, for z mode, the energies are what? Same, which is called equipartition of energy. So this is for a monatomic gas molecule, but it is also true for a diatomic. Now remember one thing, we are not talking about a single atom. Remember this, कि आपने क्या किया, आपने something which is not possible. Suppose you somehow picked up a particular atom, and that atom was moving along the x-axis, and you start saying that, sir, kinetic energy along the x-axis is present, but it's not moving along the y-axis, it's not moving along the z-axis. Therefore, how can you say that it has equal energy in all three degree of modes? So we are not talking about a single molecule, remember. We are talking about what? Energy of all the molecules, and then average of this energy. And that average again taken over a time interval. You don't have to worry about these things. A simple idea is something like this, that there are, let's say, 100 molecules. So you find energy of these 100 molecules along the x-axis. You take the average, and then you take the average again after 10 seconds. You take the average again after 10 seconds. You conduct this experiment for an hour, and then you again take the average for this 1 hour period. So this is called what? Averaging done over number of atoms, and then averaging of that over a time period. Once you do that, you will find that the sample has equal energy in all directions or in all degrees of freedom. So, write down the statement. According to the law of equipartition of energy, energy of a molecule, inside the bracket, average. दिमाग में ध्यान रखना, this is all about average, and average of average basically. According to the law of equipartition of energy, energy of a molecule for any degree of freedom is same and is given by half k t. This k is called Boltzmann's constant. What is this constant? In just a few minutes time you will understand what this thing is. So energy of each and every molecule for a given degree of freedom is what? Half kT. Remember this part, where K is Boltzmann's constant and T is what? Absolute temperature of the body, that is temperature in the Kelvin. Now, what is this? Energy per degree of freedom. You can write like this also. What is half kT? In front of half kT you can write that energy per degree of freedom. For 1 degree of freedom, energy is what? Half kT of a molecule. If you wish, you can write like this. For 1 degree of freedom, energy of a molecule is what? Half kT. For F degrees of freedom, energy will be what? Half kT multiplied by F. There are 3 You will say half kT, half kT, half kT. If there are 5, you're saying half kT, half kT, half kT, half kT, half kT. Hope you understand. Half kT, half kT, half kT, half kT, half kT, 0 kT. This is negligible. So, for F degree of freedom, you've got half kT multiplied by F. What is this? Energy of a molecule for 1 degree of freedom, for F degree of freedom. So this is basically energy of a given molecule. Now, we never talk about a single molecule, we talk about n moles. In n moles, how many molecules are present? Well, I hope you know that total number of molecules will be n multiplied by Na. Although I haven't taught you Avogadro number and all, but I know that you know these things. So, in n moles, how many atoms are present? How many molecules are present? N multiplied by Na. 6.022 into 10 to the power 23. These many molecules are present in n moles, and every molecule has this much energy. So what is the energy of n moles? What is the energy of n moles? Energy of n moles. It will be n multiplied by F by 2 kT. Energy of a single molecule for all its degree of freedom, F by 2 kT. There are n number of molecules in n moles. So energy of n moles is n into F by 2 kT. This is energy of n moles. But we already know that energy of n moles is called what? NCVT. Energy of n moles, that was NCVT. du was NCVDT. U is what? NCVT. With the help of this, we have obtained a function for CV, molar specific heat capacity at constant volume. What is the function? NT. And in this n is present. Let me write down this over here. The U you're getting is what? NCVT, which is n into Na, F by 2 kT. NT cancelled. Your CV is coming Na multiplied by K, N gone, T gone. Na multiplied by K into F divided by T, divided by 2. This Na multiplied by K is called gas constant R, F by 2. Na into K is nothing but R. Avogadro number multiplied by Boltzmann's constant is what? Gas constant R. CV in terms of degree of freedom. Now, just listen first and then note down this thing. If you remember the last lecture, I had told you that internal energy is a function of temperature. बाकी की सारी चीजें क्या हैं? Constant. N moles, CV. Now look at CV. It's just a constant. We found CV with the help of what? Isochoric process. We developed the concept of CV for isochoric, but it has nothing to do with that isochoric thing and all. CV is a constant, is RF by 2. We use CV as a number for an adiabatic gas also. So it was obtained, it was developed with the help of isochoric, because then we can easily understand everything. But CV is just a number which is RF divided by 2. Understand everything fast. For 1 degree of freedom, a molecule has what? Half kT. What is half kT? Energy of a molecule per degree of freedom. Remember this. How many degrees of freedom you have? F. So what is the energy of a molecule? Half kT into F. Energy of a molecule. Now there are n number of molecules, n into Na. That gives you U in this form. But we already know that U is NCVT. Use this and you got the value of CV. That means, look here first. What is CV for helium? If somebody says find out CV for helium, we'll say 3R by 2. Degree of freedom is what? 3. If somebody says what is CV for hydrogen, if they mention nothing, there are no vibrations present, and therefore degree of freedom is what? 5, and the answer is 5R by 2. So we have obtained CV with the help of this whole analysis. If you understand up to this point, then write down yours in the comment box. And if you have any doubt, then do mention your doubt. Now tell me fast. Get me the value of CV for nitrogen. Fast. What is the value of CV for nitrogen? कुछ खास नहीं करना है. H2 diatomic 5R by 2. So it has nothing to do with H, N or O. If it is 2, you get 5R by 2. If it is helium or argon, they both are what? Monatomic. If you have got monatomic gas, your CV is what? Same. If you have diatomic gas of every type, your CV will be what? Same. So remember this, and in fact write down as a statement also. CV for any type of monatomic gas is 3R by 2. Similarly, CV for any type of diatomic gas is 5R by 2. CV for any type of diatomic gas is 5R by 2. Now let's see who answers this. Get me the value of CP. CP in terms of R for helium and for monatomic and for diatomic. Let's see who answers these things without my help. I'm asking you CP, molar specific heat capacity at constant pressure for monatomic and for diatomic. So when you answer this thing in the comment box, you do mention monatomic and diatomic. Look here. This is CV, and everybody knows Mayer's formula. What is Mayer's formula? Cp minus Cv is R. Cp minus F R by 2. So what's the value of Cp? Cp is coming R times 1 plus F by 2. So for helium or monatomic gases, is 3, 2, 5. Cp for diatomic for diatomic 5, 7. You can also find that for diatomic with vibration. So that's the value of Cp and Cv for mono and diatomic gases. Now let's do a better thing, and let's prepare a chart so that you can easily remember these values. Complete the table. Mono, dia with vibrations, Cp, Cv, gamma. So what is this? Cp 5, Cv 3. Write down fast in the comment box. What is gamma for monatomic gas? Fast in 5 seconds. 1, 2, 3, 4, 5. What is gamma? What is gamma? Cp upon Cv. Cp upon Cv, 5 by 3. For dia, Cp is 7R by 2, Cv is 5, and gamma, Cp upon Cv. For dia with vibrations, put the value and you will find it's coming 9R by 2, 7R by 2, and this is your 9 by 7. So the thing is what? This is 3. Look at the chart, how easy it is to remember this thing. Start with CV. 3, 5, 7. 3, 5, 7. Jump off 2. CP. 5, 7, 9. 5 plus 2 plus 2. That way. And for gamma, just take the ratio of CP and CV, CP and CV. And you can expect short answer question, school examination as well as in any NEET or JEE main type examination. They can ask you things from this chart. Put on this. Now who will give me the relationship between adiabatic gas constant gamma and degree of freedom F? Give me a formula for gamma and F. First, we have the formula for CP, we have the formula for CV in terms of R and F. I want a formula of gamma in terms of degree of freedom. Get me this formula. Good. First answer, correct answer. What is gamma? CP upon CV. This is CP. Divide the CP with CV. That this becomes gamma. CP upon CV. R cancelled. Now do what? F by 2 divided by F by 2 is 1 plus 1 upon F by 2 is 2 by F. So this is the formula for gamma and degree of freedom. 1 plus 2 by F. Let's verify this thing. F is 3. 5 by 3. 5, 7 by 5. 7, 9 by 7. So this is the formula for adiabatic gas constant and degree of freedom. Alright, I'm giving you a formula for competitive examinations, and remember that if you have a mixture of gases, for example, hydrogen is mixed with helium, things like that, then for that type of thing, if we are looking for CP, CV and gamma, write down the heading. Write down the heading CP, CV and gamma for a mixture of gases. I'm giving you the formula directly. CP of a mixture is, if you have got N1 moles of CP1 type, N2 moles of CP2 type, and 3 moles of CP3 type, and so on, divided by N1 plus N2 plus N3. Very easy to remember formula, something the same format, kind of center of mass format. M1 x1 plus M2 x2 plus M3 x3 whole divided by M1 plus M2 plus M3. Basically it is what very easy to develop. These many moles multiplied by this is individual contribution. CV of a mixture, same profile, N1 CV1 N2 CV2 plus all divided by N1 plus N2 plus. Gamma of the mixture is N1 gamma 1 plus N2 gamma 2 plus whole divided by N1 plus N2. Note down this and then make a cross. This is correct. This is correct. Don't forget to write this because many times you will remember gamma also in this form. N1 gamma 1, N2 gamma 2 upon this. No. What was gamma? Gamma was a shortcut. When we developed that adiabatic gas equation PV to the power was Cp upon Cv. And that Cp upon Cv in short was called what? Gamma. So whenever you need gamma of a mixture, you will find Cp of the mixture and Cv of the mixture, and then you will divide these things. Cp of the mixture divided by Cv of the mixture. This is the correct profile. Don't forget to write this and then make a cross so that you always remember this. I'll just take 2 minutes more. I'll give you a question so that you can understand the whole profile. Take a screenshot fast and write down the question. Take the screenshot. Write down the question. 5 moles of helium. 5 moles of helium are mixed with 7 moles of argon. 5 moles of helium are mixed with 7 moles of argon. Find out Cp of the mixture. Find out Cp of the mixture. Let's see how long you take to answer this. Five moles of helium are mixed with 7 moles of argon. What is Cp of the mixture? Well, you are taking too long. You're not supposed to use this formula. Why? Because what is this? Monatomic. What is this? Another monatomic gas. In every monatomic, for us, Cp, Cvy is what? Same. What is Cp of a monatomic gas? 5R by 2. What is this? Monatomic. Mixed with another monatomic. So what is Cp? Kaun use karega formula. Even if you do that, you will get the same thing. Why? N1. Let's see the use of the formula if you want to. N1 5 multiplied by helium 5R by 2. A waste of time. 7 multiplied by 5R by 2 divided by 5 plus 7. Take 5R by 2 common, 5 plus 7 is getting cancelled. So I gave you the question just so that you remember this, that whenever you mix monatomic gases, your Cp or for that matter Cv, they do not change. Do you understand this part? Yes or no? Write down fast in the comment box. And answer is 5R by 2. Good. Write down the statement. If different types of monatomic gases are mixed, then Cp, Cv, gamma do not change. And same is the case with mixing of different diatomic gases. Same is the case with mixing of diatomic gases. If you mix 10 moles of nitrogen gas with 20 moles of oxygen plus 30 moles of hydrogen, what is Cp? 7R by 2. What is gamma? 7 by 5. When is this thing going to change? When you mix 5 moles of helium with 10 moles of hydrogen. That's a different type of combination. Now you've got what? Helium, which is mono, as well as hydrogen, which is dia. Both are present. If both are present, then use these. If combination is mono-mono, dia-dia, बेकार है फिर ये. If you understand everything in today's lecture, then write down yes in the comment box and then you can leave. Thank you very much.